Yeah, so our second poster prize winner is Yi Yim from MIT and I guess University of Texas at Austin. And she will be talking about where can a place cell put its field. Let's just count the way. Thank you very much.
Yeah, thank you for the prize and giving me the opportunity to give a presentation. I'm very glad to present my recent work today on the distribution of place fields in the place cell. And before I start, I would like to acknowledge the important people behind this project. This work would not be possible without my advisors, Ela Feed and Tibor Telefilmia, as well as our collaborator, Lorenzo Satun. Yeah, in the hippocampal formation, two types of neurons are well known for their representation of the physical space an animal is in. First is place cells. A place cell fires at very few special locations in an environment known as place fields. And the black line here indicates the trajectory of the animal in a square room, and the red dot denote the spikes. And the corresponding rate map is shown on the right. And this bump location is a place field. And the second type of cell is grid cells. They have much denser activity. And three examples are shown here. And they fire in hexagonal spatial pattern. Because of this periodicity, each grid cell can be characterized by the period of its firing pattern, which is the distance between two neighboring activity bumps. Grid cells form modules with discrete periods, and they have direct projections on place cells. So we have the two different kinds of cells. We get back to place cells again. Place cells are known to have sparse activity compared with grid cells. But in a large environment, they can have multiple place fields. The activity of 4 example place cells is shown here. And each of them has multiple place fields in this large 2D environment. And this is also true in a large 1D environment. Here are 3 example place cells activity when the animal was traversing a very long one-dimensional track. And you can see multiple multi-peak activity for these example place cells. And it is still unclear how place fields are distributed, and they may appear random. On the other hand, this makes us wonder whether place cells inherit some spatial structure in their firing from the periodic firing grid cells. So our question is, can place fields be set down in arbitrary locations, or are they structured? We start with a single place cell model in a one-dimensional space, receiving some spatially periodic input from grid cells. And the input is summed and thresholded. And we defined place fields as the location where the activity is above some threshold. To address the question more quantitatively, we consider the place cell as a perceptron. And the input is the location-specific grid cell activity pattern. As an illustration, we consider 2 grid cell modules with period lambda equals 2 and 3, a simple example. Then in this case, we can have two grid cells with period 2 and 3 grid cells with period 3. And so there are 5 grid cells in total, and they can represent 2 times 3 equals 6 locations distinctly, because beyond that, then the pattern will just repeat. And we assign place fields in the output. If the location is a place field, the output corresponding to that location is 1 and 0 otherwise. And in this example, we want locations 1 and 5 to be our place fields. And this output vector, Y, indicating place fields and non-place fields, is called a field arrangement. And then we can train this network by searching for a set of weights W that can realize a given field arrangement. And in that example, we can find a set of weights given here to realize location 1 and 5 as our place fields. And so this field arrangement is realizable. However, not all field arrangements can be realized. An example is shown on the right. You cannot find a set of weights W to realize location 1 and 6 as place fields. Mathematically, this is a question of linear separability. If there exists a hyperplane that can separate the two classes of patterns, then the given arrangement is linearly separable. Otherwise, it is not. So get back to our grid cell input. Our patterns are the locations represented by the column vector. In this example, these pattern sets form a triangular prism. Connecting to our previous examples, we can draw a hyperplane, here the shaded color hyperplane, to separate location 1 and 5 from the rest of the locations. That's why this field arrangement is realizable. But we cannot draw a hyperplane to separate location 1 and 6 from the rest. Therefore, 1 and 6 cannot be the only place fields. And more generally, the set of grid codes are vertices of a convex polytope. And this holds true for not only for periods 2, 3, but also for other different values of periods and also different number of modules. And we can count the number of arrangements that are realizable. And indeed, in 1965, Cover did this for random input. And this axis shows the fraction of realizable arrangements with p random patterns. One thing to note here is that in n-dimensional space, the fraction is 1 for p smaller than or equal to n. And beyond that point, the fraction drops below 1. And this is for random input. So we get back to our grid cell input, which are spatially structured. And so with p locations, we will have 2 to the p possible field arrangements, which is a big number in a large environment when p is big. And then we can do the same thing. We count the number of realizable field arrangements with grid cell input. And the general trend is that with a few locations, and all field arrangements can be realized, meaning that place fields can be arbitrarily placed. But as the number of patterns or locations increases, the realizable fraction drops below 1, meaning that not all field arrangements are realizable. And you can imagine having only like a few patterns in a space of fixed dimension. Everything is linearly separable. But when you put more and more patterns in the same space, at some point, not all of them are linearly separable anymore. And there's a critical point called separating capacity in computer science, which is the maximum number of patterns that all field arrangements are realizable. And we made an estimate on how large this separating capacity is with grid cell input. Given m grid modules with period from lambda 1 to lambda m, we derived a formula for the separating capacity using the inclusion-exclusion principle. I'm not going to show you the derivation today. I just want to point out that it is bounded from above by the sum of periods. And on the other hand, the range of grid codes somehow gives the number of locations that can be distinctly represented, and so provides a rough estimate of the range of locations an animal can represent distinctly. And it is approximately the product of the period, which is much bigger than the sum of periods or the separating capacity. And this result implies that if grid cell input is the main drive of place cells, place fields cannot be arbitrarily placed. And if the place field locations are not arbitrary, our follow-up question would be, can they be predicted? We can estimate the number of realizable field arrangements for 2 grid modules using combinatorics. So the number of realizable field arrangements with 2 grid modules of period lambda1 and lambda2 can be expressed like this, and it turns out to be a polynomial number. And for large periods, lambda1 is of the same order of magnitude as lambda2, so we can do some approximation. So we will have approximately 2 lambda cells and lambda square distinct locations, and the number of realizable field arrangements can be approximated by this. And also this 2 to the lambda square will give us the total number of field arrangements. And when this lambda is big, the number of realizable field arrangements is much smaller than the total number of arrangements, meaning that realizable field arrangements just make up a small fraction, but still this number is still big. So we cannot really predict the place field locations. Okay, and an interesting question related to the grid cell input is, are those realizable field arrangements generated by grid code robust? And we go back to the idea of linear separability. We have 2 classes of patterns here, and many hyperplanes can separate the 2 classes. The hyperplane is not unique. But there is a hyperplane that can separate the patterns with the maximum margin. And the larger the size of this hyperplane, the more robust is the arrangement. Therefore, we characterize the robustness of the place field arrangements by this margin. And we can consider it as the distance between 2 classes of patterns. So go back to our grid cell input, and we take into account that place fields are sparse. So we consider, again, 2 modules with large periods given here. So with these 2 periods, we can, so over like over 1,300 locations can be represented distinctly. As the place fields are sparse in place cells, we consider, we compute the margins for a field number of place fields. Let's say from 1 to 0, sorry, from 1 to 6. And the margins with grid cell input are represented by the black bars here separately for different number of place fields. And we compare them with the margins with the shuffled version of the grid cell input, as well as the margins with random input represented by the pink and the blue violins respectively. And as you can see, with grid cell input, the margins are bigger in general, meaning that the place field arrangements with grid cell input are more robust. So here comes our summary. Place field locations are highly constrained, and the realizable place field arrangements only represents a tiny fraction of all potential arrangements, but the number is still big. And the place field arrangements generated by the grid code are more robust than those by random code. Yeah, that's all. And I'm happy to take questions.
Thank you. So, other direct questions at the moment? So, as Daniele recalled, you can raise your hand, ask question in the Q&A or directly on Slack. Okay, I'm not seeing any at the moment. Okay, well, what I suggest is that if there are not much question, we'll just continue the poster session. And we'll thank you once again